Okay, let's start our section on measurement by talking about the metric system. All right, there's a lot of different reasons for using the metric system. Most people in this country, of course, are familiar with the English system with feet and pounds and gallons and things like that. And those are fine, but for scientific work, we almost always use the metric system because there are a lot of advantages to that. The first one is that it is an internationally recognized set of units. So a person can be writing in India or Zimbabwe or France or Russia or China or the United States, and the measurements that they record with units will be understandable to people all over the globe. And that's really helpful, particularly now that science has become kind of a global endeavor, right? We don't have just random people working in their own garages like we had in the alchemists in medieval Europe several hundred years ago. Another advantage is that you can write numbers in a way that looks very, very simple and compact. And specifically, using the metric prefixes, you can write most values as a number between 1 and 1,000, and then adding the necessary prefix to move the value into that range. And numbers between 1 and 1,000 are just a lot easier to use, they're easier to say, they're easier to read. For example, 72.5 is a lot easier to digest than 0.000000775. I forget what number I gave, but whatever it is, it's a lot easier without all those superfluous zeros on either the right or the left hand. All right. Also, calculations are a lot easier. As you know, if you're converting between feet and inches, you're going to have to multiply or divide by 12. Going between pounds and ounces, you've got to multiply or divide by 16. That's not super difficult, but it's tricky, and generally speaking, you wouldn't want to try to do that without a calculator. When you're working with the metric system, you can do all of your unit conversions just by moving the decimal to the left or the right, and you can do that without a calculator. That makes things much, much nicer. And the last thing is that all of the different things that we measure can be expressed in terms of a few different kinds of units. So we don't need a unit for speed and a unit for force and a unit for pressure and a unit for length and all that kind of stuff. We can define all of the different things that we'd be measuring in terms of about a half a dozen units. All right, let's take a look. All right, so here are the units. We call this the metric system, but sometime in the middle of the 20th century, this was codified by a group and recorded as the Système International des Units, which we say is the International Unit System. And because of this acronym, it's in French, right? We often call these SI units. So we want to record our values in SI units when possible. All right, and some of these you're familiar with. The SI unit of length is the meter, and that has the symbol lowercase m. Right? The unit of mass is the kilogram. Kilogram is a little more than 2 pounds. Unit of time is the second, and second has two accepted abbreviations, either S or SEC. I would say depending on clarity. Sometimes it's just easier. Obviously, it's easier to write S because it's shorter, but sometimes if you've got a collection of units, SEC makes things look a little bit more clear. So people use both of those. Temperature, the SI unit is kelvins, right? But we also often use Celsius. We'll talk about that in a little bit. The unit for chemical amount, which just means the amount of any substance, is the mole and has the abbreviation MOL. We'll talk about moles a lot once we get to structure of the atom and molar masses and formula weights and things like that. For electrical current, it's the ampere or the amp We won't use this very often. We might get into this in the electrochemistry chapter. Generally speaking, probably won't see that until maybe next semester. And finally, luminous intensity is the candela. And I will tell you that unless you're in physics and you're looking at light, you'll probably never see that. I'm 52 now, and I don't think I've ever done some kind of a measurement or read a paper or worked on something that included candelas as a unit. So I'm putting it there because it's part of the table. It's one of the SI units, but you won't see that, and I won't test you on it because it's just not important for what we're doing. The others, and actually amps, you won't see for a while. I wouldn't test you on amps until we get to the point where we're actually using amps. Okay, the others you should know. All right, so in addition to the units, we've also got prefixes, and here is a nearly complete list of prefixes. There are some smaller prefixes that would go off the bottom of this table and some larger ones that go off the top, but it's very rare that you need prefixes larger or smaller than these. So this is essentially the group of prefixes that I would like you to know. I will also mention these two here, hecto and deca, are almost never used. Like before, I would say I can't really think of an example where I've heard someone talk about hectograms or hectometers or anything like that. So I'm like before, I'm including it here because if you look up a table of metric prefixes, you'll see that in there. So it is an accepted and defined prefix, but you will almost never see it, and I will not test you on it because you're not going to see it, right? Same thing with deca. Deca in particular, I think, is problematic because deca sounds so much like deci, right? So deca, again, rarely used. I can't think of a time that I've seen it. So it's part of the table, learn it, but I'm not going to test you on it. All right. Then for the other units, all of these prefixes are applied to some kind of a base unit. For example, if you're talking about weight, then the base unit, or mass, I should say, talking about mass, the base unit would be the gram. And so you have prefixes for weights that are larger than a gram, so kilogram, megagram, gigagram, and teragram. And you have a set of prefixes for things that are less than a gram, decigram, centigram, milligram, microgram, nanogram, and picogram. Okay. These two here, kind of like before, deca and centi, they're not used very often, but they do appear from time to time. Centi in particular is actually pretty common. Deci, not very often. I would say leave these on the table, and I would commit those to memory with the rest of the prefixes. But also, if you take those out, let's ignore those for just a moment. If you ignore these guys, right, then you'll see that all of these units vary by a factor of 10 to the 3, right? So this is 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. You go in the other direction, 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12, right? So that means that each one of those prefixes varies by a factor of 1,000, right? So if you're going in this direction, mega is 1,000 times larger than kilo, giga is 1,000 times larger than mega, and tera is 1,000 times larger than giga. And going down this way, micro is 1/1000th of milli, and nano is 1/1000th as much as micro, and pico is 1/1000th as much as nano. All right. Okay, make sure you are familiar with all of those prefixes. We'll use them fairly often. Okay, so let's look at how to use metric prefixes to write a number in a way that's a little bit more convenient, so that we can get that number into that range between 1 and 1,000, so we don't have those superfluous zeros on either end. All right, so first, every time you change, as you look at those prefixes, all of them except for deci and centi, they represent a factor of 1,000 change in measurement. And that's what we were saying on the last slide, right? And so if each of those changes in prefix represents a change of a factor of 1,000, then that means that's equivalent to moving the decimal either to the left or the right by 3 positions. And what you want to do when you're changing the prefix on a number is you want to keep the ultimate value the same. So if you change the prefix so that the prefix becomes larger, you have to change the number to make it smaller. And vice versa, if you make the number larger, you have to make the prefix smaller, so that the combination of the number and the prefix together will have the same value. Okay. All right, let's look at an example. A sample of tuna fish is analyzed and found to contain 0.0025 grams of mercury. We want to write this in a form that is simpler using a metric prefix. All right. So what we want to do is we want to get rid of these extra zeros here that we don't need. So let's remind ourselves of our scale, our base units, kilo, mega, giga going up, and micro. Something I probably should have mentioned on that last page. We got 3 different M's here: micro, or milli, micro, and nano. Okay. There are 3 different M's as these prefixes. Mega up here, I didn't do a very good job drawing this, but mega is a capital M. Milli is a lowercase m, and micro is actually the Greek letter mu, which is the Greek equivalent of an M, right? So there are 3 different kinds of things that are essentially M's, but they're written differently, and recognize the difference between milli, micro, and mega is obviously going to be important. Redraw that one a little bit better. All right, so let's change this value here so that we can get rid of those zeros. Okay, so what we want to do is move the decimal so that we don't have any extra zeros on either the left or the right. Doesn't mean we won't have any zeros, but we don't want any more than we need. So to get this number 0.0025 into a range that we like, we need to move the decimal, and by using these prefixes, each time we do this, we're changing this by 10 to the third or 1,000. So we have to move the decimal in units of 3 spots. Right? If we move the decimal over that way, we'd be putting in extra zeros, and that's no good. That's not going to help us. That's going to make the number look even more confusing. Right? So to make the number look a little bit nicer, we want to move the decimal to the right. So if we move it over 1, 2, 3 times, then we get 2.5. And because we changed the number from 0.0025 to 2.5, we made the number bigger. That means we have to make the prefix smaller. And since we went 3 spaces, we have to go down 1 prefix. So go from our base unit to milli. So that means 2.5 milligrams is our answer. Later, I'll just mention, we're going to do a couple more of these. Later, when we talk about dimensional analysis, we'll see a different way to do this, which works as well. Maybe arguably works a little bit better. It's a little bit more consistent with our other calculations. But I think in the meantime, it's helpful to practice doing it this way, moving the decimal and changing the prefix. All right, here are a couple more. What I would ask you to do, let me remind you of the list of prefixes over here. There are 4 problems here. Give each one of these a try. Hit the pause button. Try these and see what you get, and then unpause the video and I'll show you my solutions. We'll work through some of them, maybe not all of them, but we'll look at them. I'll show you my solutions for some of these. All right, so let's look at the first one. It says we've got 65 milligrams of caffeine, and we want to express this in grams. Okay. So if we look at our units over here, if we're going from milligrams to grams, we're going from milli to the base unit, right? So that means we are increasing the value by a factor of 1,000 by this change in prefix. And so if we increase the value of the prefix by 1,000, we need to decrease the value of the number by 1,000, and that means move the decimal 3 places to the left. Right. So if we put our decimal here, it's 1, 2, 3. So our result would be 0. Oops, not enough room. Our result would be 0.065 grams. All right, now let's do the same thing with a golf ball. This time we're going in the other direction. Golf ball is, actually, are we going the other direction? Oh, yeah, we're going both directions actually for this one. Golf ball is 45.9 grams, and we want to convert this to kilograms. All right. So in this case, we're going from the base unit grams, we're going up 1 level to kilograms. And just like last time, if we move up 1, we've increased the value by 1,000 by virtue of having put that prefix there. So that means we've got to make the number itself smaller by a factor of 1,000. So therefore, this will be 0.0459 kilograms. Okay. Now, if we go in the other direction, it's also asking us what this is going to be in micrograms. So we've got, oops, don't need that. .9 grams, and we want to go to micrograms. That means we're going from the base unit, and now we're going 2 steps, right? We're jumping down 2 prefixes, right? So that means this is 10 to the 3rd, this is 10 to the 3rd, so that whole jump is 10 to the 6th. That means we've got to move the decimal 6 spots. And we've got to move it 6 spots, and because we're going from grams to micrograms, we're making the unit smaller. That means we're going to have to make the number bigger. So to make the number bigger, so let me erase here. We've got to move the decimal 6 times. 1, 2, 3. 1, 2, 3. So that would be 45,900,000 micrograms. Okay. All right. Let's do, well, Well, you've done number 3. This might be kind of hard to see on your computer. There are 9 zeros here, right? 0 point, and then 9 zeros, then 113. And when you convert that from meters to, well, let's see. Okay, let's do this one because this one is a little bit different. We don't actually know what unit we have to use, so we'll have to go the other direction. We'll move our decimal first and then figure out the units. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. All right. Now to get this as a reasonable number, that is a number between 1 and 1,000, we'll move our decimal over. I'm going to do jumps of 3 here. There's 3. There's another 3. There's another 3. And there's another 3. So I have moved the decimal 3 spots 4 different times. So I've got to change my prefix by 4 steps in this table here. And since I made the number bigger from 0.00000000113, I now made the number 113. So if the number is bigger, I got to make the prefix smaller. So I'll go down here 1, 2, 3, 4 times. So 113 picometers. All right. And then I'm going to do this one too, although I'm only going to do the last part. I'm going to do the micrometers part. You can do the gigameters yourself. To go from kilometers to micrometers. The reason I wanted to show you this one is because kilometers and the micrometers are on opposite sides of the base unit. Right? So I wanted to point out that as you go from here to here, you have to count that base unit in between. So I moved the decimal 3 spots to get from kilometers to meters, and then 3 spots again. Oops, not 3 spots. And 3 spots again to get to millimeters, and then 3 spots again to go to micrometers. Right. So it is actually 9 spots that we have to move that decimal. And since we are making the unit smaller, we have to make the number itself larger, right? So here's our decimal. We've got to move it over 9 times. Again, I'm going to do it in jumps of 3 this time. 3, 2, 3, 2, 3. So this would be 6, 3, 7, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. What is that? Is that 6 trillion? Yeah, 6,371 million micrometers. And if you did the gigameters, you should have gotten 0.006371 gigameters. All right. Okay, a couple of other units to discuss. Temperature, as I said before, the standard SI unit of temperature is kelvins. And something interesting about kelvins, Kelvin is capital K, but even though it's temperature, there's no degree symbol. So people often say degrees Kelvin, and I wouldn't be bothered if you said that. But technically, we should not say that. We should just say Kelvin. The temperature is 273 Kelvin or 273 kelvins, but not 273 degrees Kelvin. Okay. Celsius, however, which is more common which we usually actually do use Celsius. Celsius is written with a degree symbol. And the difference between Kelvin and Celsius is a matter of 273 degrees, or units if you want. Right? And so anytime you're converting from Celsius to Kelvin, you just have to add 273, and anytime you're going from Kelvin to Celsius, subtract 273. The reason for that is that if you use the 273, then 0 Kelvin here will correspond to absolute 0, which is the lowest possible temperature. All right, you should know a couple of important temperatures. You should know that, well, you should know absolute 0, right? I just wrote that over there on the side, but it's actually here in the table too, right? You know, absolute 0 is 0 degrees Kelvin, which of course is, if you just do the math, right, it's got to be negative 273 Celsius. You should know that water freezes at 0 degrees Celsius, or 273 Kelvin. And even though we don't use Fahrenheit very often, this is an important enough number that you should probably know that water freezes at 32 degrees Fahrenheit. Room temperature is not really a well-defined number, but just as kind of a common agreement, scientists have decided that room temperature, or normal temperature, or typical temperature is about 25 degrees Celsius, or 298 Kelvin. And then the boiling point of water, you should know, is 100 degrees Celsius. So if you add your 273, obviously that's going to be 373 Kelvin. And for Fahrenheit, you should know that that's 212 Fahrenheit. Again, mostly just because we all live in a country where people usually use Fahrenheit, and we should know the value of these two very important points on the temperature scale in Fahrenheit. All right, so be able to, also I've got this equation here. I put this up here just because people like to do that. It's in your textbook. You don't have to memorize that equation. I'm not going to ask you to use that to convert between Fahrenheit and Celsius. If you want to use it, you certainly can, but you won't be doing a lot of Fahrenheit to Celsius conversions, although you will do a lot of Celsius to Kelvin conversions. So you definitely have to know this. All right, there are a couple of other non-standard units, and these are important. The first one is the angstrom, and the angstrom is a unit of length used for measuring or describing the sizes of atoms and molecules. And the symbol for the angstrom is a capital A with a little circle on the top. And so that is 1 angstrom, and 1 angstrom is 10 to the minus 10 meters. Fortunately, that number 10 to the minus 10 is fairly easy to remember, or at least I always thought it was easy to remember. And an angstrom is approximately the diameter of most atoms. You know, hydrogen, smaller atoms up at the top of the table have diameters of approximately 1 to 2 angstroms. And on the topic of length, I'll also mention the micron. A micron is really just another name for a micrometer, or some people say micrometer, right? And so this is just 1 micrometer. It's just meter with the prefix micro on it, right? And so that means that that is 10 to the minus 6 meters. Micron is not used very often in chemistry. It's used a bit in physics and biology. So I'm really putting it here mostly just, I'll put it in parentheses, putting it here mostly just for your information, because you may see that term, and people often use the term micron without defining it. So I wanted you to know what that means. But since we don't use it in chemistry, and it's not a accepted SI unit, I won't be testing you on that one, but I just wanted you to know what it meant. Another one that is important is a liter, and a liter is defined as 1 decimeter cubed. So decimeter, here's one of the times where we're using that prefix deci. Right? A decimeter is 1/10 of a meter, or 10 centimeters, which is about 4 inches. So if you had a cube that was 4 inches on each side, the volume of that cube is 1 liter. The standard unit of volume in the metric system is actually the cubic meter. And sometimes when you look things up in tables, you'll see the volumes given in cubic meters. But because a cubic meter is actually pretty darn big, a lot of times when values are listed in cubic meters, like if you list the mass of an object in grams per cubic meter, you end up getting really, really big numbers because a cubic meter is so large. So it's a lot more convenient in most cases to use liters. And so although liters are not an SI unit, they are accepted. In fact, they are by far the most common unit in chemistry for volume, the liter. All right. I'll also mention that because this is 1 cubic decimeter, right? Decimeter is 1/10 of a meter, and so this is 1 decimeter across here. It's also 10 centimeters. So if you had a cube that was 10 centimeters on each side, the volume of this would be 10 times 10 times 10, which is 1,000 cubic centimeters. Okay. So this means I'm looking for a space to write. I guess I can, you've already written this down. I can wipe this out. All right, so that means that 1 liter is 1,000 cubic centimeters. And when we write cubic centimeters, we always write it centimeters cubed, but sometimes, particularly in biology and medicine, cubic centimeter has the abbreviation cc. So like if you're watching a medical drama on TV, they might say, give him 5 cc's of Haldol or something like that. I don't know. I just made up that name. But anyway, so a cc is the same as a cubic centimeter, which is the same as cm cubed. Right? And because there are 1,000 cubic centimeters in a liter, a cubic centimeter is the same as 1/1000th of a liter. So that means that 1 centimeter cubed is the same as 1 milliliter. Okay. I'm going to erase a little bit. And rewrite that part, because it was getting really cluttered. That's the word I was looking for. All right. So 1 liter is defined as 1 decimeter cubed. And this is 1,000 milliliters. Which is the same as 1,000 cubic centimeters. Oops. Which is the same as 1,000 cc's. Okay. We won't use, I'll put this one in parentheses. We won't use this one in this class, but you might see it in other places. And also I just wanted you to know what it was in case you hear it on TV and stuff like that. All right. So You should know the definition of a liter is 1 cubic decimeter, and that there are 1,000 milliliters in a liter, and that means 1,000 cubic centimeters in a liter. Oh, and one other thing. We'll look at this in more detail a little bit later when we talk about conversions, but 1 liter is approximately the same as a quart, right, or 1/4 of a gallon. All right, then there's one more unit, and that is the metric ton. Right? And 1 metric ton is defined as 1,000 kilograms, right? Which would just be, if you look at the units, the prefixes, right, that'd just be 1 megagram, but no one says megagram, they say metric ton, right? And so, because 1 kilogram is 2.05 pounds, and again, we'll look at these conversions later. Because 1 kilogram is 2.205 pounds, that means 1 metric ton, or 1,000 kilograms, is equal to 2,205 pounds. And the reason it's called a metric ton is because this is very close to 1 US ton, which of course is 2,000 pounds. All right, so excuse me. So summarizing this, what you should know from this video lecture, you should know all of the base units on that first table, meter, kilogram, moles, Kelvin, second. I wouldn't worry about amps right now, and definitely don't worry about candelas. We won't be seeing those in this class, but you should be familiar with the others. Make sure you know the names and the symbols and the values, right? The prefix here, or the numerical 10 to the 3, 10 to the 6, 10 to the 9, 10 to the minus 3, minus 6, minus 9. Know how all of those are related to the different prefix, and remember the both the names and the symbols. In particular, the one that I mentioned before, which can be kind of tricky, mega is capital M, milli is lowercase m, and micro is mu, which is the Greek letter M. Right. I think most of the other prefix symbols all make pretty much perfect sense, right? They're all sort of phonetic. All right, and then you should be able to, as we did a little bit of practice with this, you should be able to convert the form of numbers by changing the prefix and moving the decimal to the left or the right. Generally moving that 3 spots at a time for each prefix. When you're counting the prefixes to see how far to move it, you have to skip over deci and centi, because those are 10 and 100 respectively. And then finally, know the non-standard units that are not part of the SI system but are still used very, very commonly. Liters, milliliters, cubic centimeters, centimeters cubed, Kelvin and Celsius, angstrom, and metric ton, right? These are all things that are used commonly, and you should understand what those units mean. All right, terrific. All right, thank you for sticking with me through that lecture, and we'll be back with another one in a little while.